Okay, so last time we were starting to talk about we've been continuing to talk about the frequency response of our current mirror differential amplifier in various ways. And you might have been wondering, why are we just thinking about the output capacitance of this thing? Why not consider some sort of internal capacitances? And that's a fair question. And so I'd like to spend a little bit of time now trying to address that. So first thing we're going to do is put our current mirror differential amplifier back up here. And we've got, say, VCM, VCM. And we're going to go back to thinking about the differential mode gain, where we put a delta VDM in here, and we consider what is the delta V out. So we've got a VB, we've got our MB, M1, M2, M3, M4, M5, M6, M7, and M8. And we have our output capacitance C out. And so the question is, why not consider some sort of internal capacitance in here? Why just put in an output capacitor on here? And what I'd like to do to try to get an intuition for what's going on with these other capacitances is to, let's suppose we were to put a capacitor here on this node, call this C7. And what this would model, this is not we wouldn't actually put a capacitor like an explicit capacitor in the circuit here. This would model basically the gate capacitance, gate to bulk capacitance of transistor M7, the gate to bulk capacitance of transistor M8, capacitance seen looking into the gate, would model the drained to bulk capacitance, which is the effective capacitance of the drain to body diode on M7. There's also a drain to body diode on M6 that's wired to this node. There's some interconnection capacitance associated with the wires that actually connect up these various structures in the circuit. And we can lump all of those together, since capacitors combine by adding in parallel, into a single effective C7. And we would like to see or think about, what difference would C7 make in terms of our analysis of the differential mode gain of the circuit. Okay. So we're going to apply node fixing just like we've been doing and say what difference would the presence of this capacitor make in our analysis. And the first thing I want to do is consider what effect would C7 have on the output impedance of the circuit. So we've had an early effect resistor, RO8 and RO4. That we figured we needed to conclude that the low frequency incremental output impedance is not infinite to get a finite low frequency differential mode gain. And if we were to imagine having our output voltage source connected here that we're using to probe the differential mode, or rather the output impedance, by changing V out by some delta V out and looking at how much delta I out goes back into the circuit, I think it's pretty evident that if we were to go to the trouble to repeat the whole source splitting thing here with our four things and the added fifth thing connected to the output, splitting those into separate lines with replica sources here, the C out, and the early effect resistance and the two drains here, we would come to exactly the same Z out that we had a couple of videos ago, because effectively this capacitor over here is completely isolated from what's going on at the output node of the circuit. And so our Z out would still be Z out, which is delta V out to delta I out, would still be basically RO4 parallel RO8 in parallel with 1 over j omega C out. So that is unchanged by the presence of C7. And so then the real question is, what happens when we look at the GM part of the calculation, and how does this C7 come into that play into that? And so for that GM part of the calculation, we had decided that we didn't need these RO8 and RO4. I mean, we can actually leave them there. They don't hurt anything. And we'll just do the calculation with those there. The output voltage is held fixed, and we're interested in what is the delta I out that we get when we put our delta V dm into, let's say, M1. Okay? Only this time we have C7 in the mix. Well, just like before, we're going to get a delta I1 in transistor M1 because we're changing the gate voltage here. And we need to trace through what this delta I1 does in the circuit as it goes toward the output. And we're interested in how much current comes out of the circuit as a result of this delta I1. Well, the delta I1 is going to be mirrored by M3, M4, just like it was before. And we would argue that all of this delta I out, or delta I1, is going to come out as output current instead of going anywhere else. And the reasoning is the same as it was before. You might think, well, some of it could go down, could go back up RO4, and it can't because we're holding the output voltage fixed, and in order for the current flowing through RO4 to be able to change, you have to change the voltage across RO4. And because V out is held fixed, and because the top part of RO4 is held at the power supply, VDD, the voltage across RO4 is not changing, so no current can be diverted through RO4. No incremental current can be diverted into RO4. Likewise, that's also true of RO8, because the voltage across RO8 is being held fixed. We can't admit any change in current in RO8 because the current through the capacitor is C out dV out dt, and dV out dt is 0. There can't be any current flow through the capacitor when the output voltage is being held fixed. And so all of this delta I1 coming from M4 is output current. It all goes into the delta I out. Okay? So that's the same as it was before. This delta I out also flows out of the source of M1 and back up the source of M2, just like before. Flows out of the drain of M2 and is mirrored by M5, M6. Okay? So here's where things start to get a little more interesting, because we come now to the node that C7 is connected to. And we got to say, where is this current delta I1 coming from? Well, it's coming from basically two places. It can come from C7, or it can come from the current mirror, M7, M8. And so we have here a two-way current divider. Some of it will come from the current mirror. We could call that alpha times delta I1, where alpha is going to be a current divider ratio, and 1 minus alpha of it will come from C7. Okay. It might be a little more intuitive if the current were being sourced onto this node, and some of it would go this way and some of it would go this way. If you like, we just have a negative input current, and so some of it's coming from here, some of it's coming from here, but we have only a fraction of it that's coming from M7, and some of it is being supplied by C7. And so instead of mirroring delta I1, what M7, M8 mirrors is alpha times delta I1. And so what comes out of the circuit here is now alpha times delta I1. So whereas before we had 1 plus 1 times delta I1, we now have 1 plus alpha times delta I1. And so we're going to have to figure out what is this alpha. Okay, so for the GM part of the calculation, we have that delta I out is equal to 1 plus alpha times delta I1. And what is this alpha? Well, alpha is a current divider ratio, and we can express that in various forms, just like we had seen earlier in the course when we were talking about resistive circuits. One form would be the conductance of the branch, whose current we would like to know, divided by the sum of the branch conductances. And that's going to be convenient because we know the conductance of this branch is going to be just given by GM7, the transconductance gain of M7. Remember, that is the amount by which the gate voltage has to move in response to a change in the saturation current flowing through the transistor. So it's going to be GM7 divided by the sum of the two branch conductances. So that the one branch conductance, of course, is GM7, and the other branch conductance is going to be what's called the admittance of the capacitor. That's 1 over the impedance of the capacitor. And so that's going to be J omega C7. Okay, so we have here basically a frequency-dependent current divider ratio. And that's going to give rise to a factor in the frequency response. Okay, so this is still times delta I1, so this here is, if you like, alpha. And the delta I1 is going to be given just by what it was before, GM1 times delta VDM divided by 1 plus GS1 times whatever the impedance is down here, the incremental impedance, and that's still going to be 1 over GS2. And we still have the balance condition as our quiescent condition, so GS1 equal to GS2, and that means that this thing down here is just 1 over 1 plus 1, which is 1/2. And so this is going to be, if we combine these things over a common denominator, we are going to have GM7 plus J omega C7 plus GM7 upstairs. And so we're going to get 2 GM7 plus J omega C7 divided by GM7 plus J omega C7 times, well, here we have again GM1 over 2 times delta VDM. And When we have a frequency-dependent polynomial upstairs or downstairs in a frequency response like this, what we should always think about doing is normalizing the constant term. So there's a polynomial in j omega, or if you're working with Laplace transforms, you would have s instead of j omega. And what we would like to do is take the term that does not depend on j omega, and is just a constant, and factor that out, whatever it is, to make the constant term in the polynomial 1. Okay, and so we're going to factor a 2gm7 out of the numerator, and we're going to factor a gm7 out of the denominator, and we'll see what effect that has. So we're going to have a 2 gm7 upstairs and a gm7 downstairs from our factored out term. And then we're going to have a 1 plus j omega c7 divided by 2 gm7. And downstairs we have a 1 plus j omega c7 over gm7. And we have our gm1 over 2 times delta v dm. Okay, so now a number of things happen here. We have the gm7s canceling. We have a 2 upstairs, just like we had without the c7, canceling with the 2 down here. And so at the end of the day, we have, we're going to move the gm1 over here. We have a gm1. And then we have this rational function, this bilinear function, which is 1 plus j omega c7 over 2 gm7. And downstairs we have a 1 plus j omega c7 over gm7 times delta VDM. And so our GM of the circuit as a whole is now a function of omega. It's frequency dependent, which is equal to delta I out over delta V dm. That's going to be just little gm1, which it was before at low frequencies, times this frequency dependent factor, which is 1 plus j omega c7 over 2 gm1, or gm7 rather, sorry, over 1 plus j omega c7 over gm7. Okay, and the z out here, if we were to expand, parenthesize the parallel combination this way, where we keep the RO4 parallel RO8 grouped, and we have the parallel 1 over j omega c out, we saw at one point that if we expand this out as product over sum, this wound up being RO4 parallel RO8 over 1 plus j omega RO4 parallel RO8 times C out. And so if we were to combine these by node fixing, we'd have that the differential mode gain, which is delta V out over delta VDM, would be equal to GM times Z out. And so we would have, combining the low frequency terms here, I guess I should mention here that by normalizing this constant term to unity, when we're at low frequencies, all of the terms that are some power of j omega are negligible compared to 1 because omega is small. And so by normalizing these polynomial factors or terms to the constant term to unity, what that exposes is the prefactor is the low frequency behavior, and that's actually a very good way of expressing these things. It's a very nice way of doing so because a lot of times we maybe have already looked at the low frequency behavior, are interested in the low frequency behavior, and then we're interested in seeing how these capacitors or other impedances will shape the response as a function of frequency as we go to higher and higher frequencies. And so we would pick up here our normal low frequency gain, which was GM1 times RO4 parallel RO8. And now we have two frequency dependent factors. We have the one that came from the output impedance, and we have now a pole in the response due to the GM, due to the presence of this C7, and we have a 0. And it's going to be a left half plane 0, because the location of the frequency that makes the numerator term go to 0 is going to be in the left half plane. It's going to have a negative real part, and so we have in the numerator 1 plus j omega C7 over 2 GM1, 7 rather. And downstairs we have a 1 plus j omega C7 over GM7, and our 1 plus j omega RO4 parallel RO8 times C out. Okay, so this would be what is the differential mode gain of the circuit in the presence of this extra capacitor C7. So C7 introduces these two factors that we didn't have before. One is going to be a 0, and one is going to be a pole. And it's interesting to think about, you know, at what frequencies do these new factors come into play. Okay, so if we think about this RO4 parallel RO8 times C out, that's an RC product. It's a time constant, right? And C C7 over GM7 and C7 over 2 GM7 are both also RC products. It's a C over G, which is the same as an RC, right? If I divide by conductance, that's the same as multiplying by the reciprocal of it, which would be a resistance. And so these are all going to be time constants. And if we say, you know, how do these time constants, C7 over GM7, compare to RO4 parallel RO8 times C out? What can we say about that? Well, we can certainly say that, you know, the time constant of the 0, which is C7 over 2 GM7, is exactly 1/2 of, or 1 octave above in frequency, C7 over GM7, because they just differ by a factor of 2. That's obvious. But to think about, you know, what is the time constant here that's due to the output node versus the time constant here, which is in some sense due to or associated with this node here. Well, we can say a couple of things. One is that certainly GM7, 1 over GM7 is going to be a much lower resistance than RO8, right? So if GM7 is the same as GM8, right, they're matched transistors. They have the same current flowing through them because they're a current mirror, so GM7 and GM8 are going to be the same. And so if GM8 RO8 is much bigger than 1, we know that 1 over GM7 is going to be a much smaller resistance than RO8. Okay. And so RO4 parallel RO8, while that's less than RO8 by maybe about a factor of 2, 1 over GM7 is going to be a fair bit smaller than RO4 parallel RO8 in terms of a resistance. Okay, so this is going to be associated with a smaller R. This one's going to be associated with a larger R. What can we say about C7 versus C out? Well, this is an internal capacitance. It's due to local wiring and sort of the parasitic capacitance of the gates of these transistors and the diodes that form the source, or the drain to body diodes of these two transistors. This is a local interconnection, and probably will be a fairly small capacitance compared to what you might find at the output of the circuit. This output capacitance will have a component that's due to the drain to body diodes of these two transistors, just like these two over here. But these transistors, since they're the output transistors of the circuit, they might be larger, and so their drain to body diodes may be larger and hence have proportionally more capacitance. This may fan out to some larger area of interconnect because it's the output of the circuit, and it may go all over the chip or something like that, or it may go off chip. It may actually be driving an explicit output capacitance, or the capacitance of a pad, a bonding pad, or something off chip. And so Cout is likely to be a much larger capacitance than C7. And so we have two things going here that allow us to say something about the relative sizes of these two time constants, and hence, at what frequencies these factors become significant. We have here small capacitance times a small resistance, and we have a larger resistance compared to this one times a larger capacitance compared to this one. And so we get the sense that this time constant is going to be much less than, or much larger than, this time constant, and hence this pole frequency, or this pole, will kick in at a much lower frequency than this pole, and this pole kicks in at 1 octave below this 0. Okay, and in point of fact, that basically means that this capacitor sort of affects the behavior, the frequency response of the circuit at a much higher frequency than this capacitor does. And often we're interested in what's called the dominant pole, which is the pole that kicks in at the lowest frequency. And it's really that pole that determines the dynamics of the circuit and the stability of the circuit. And if we're interested in any of the other poles, we're interested in where is the first non-dominant pole relative to the dominant pole. And so we can't, practically speaking, take into account all of the capacitors in a circuit. We wouldn't want to in a sort of analytical calculation like we're talking about here, because the computation would be hopelessly complex, and our expressions would, even with good analytic techniques, would quickly become very unwieldy. And so we're interested in putting just enough complexity into the model to do the work we need to do. And so we can use some common sense in terms of, how big are these capacitors likely to be, and if we have the actual physical design of this amplifier circuit down at the transistor level, we can estimate some of these capacitances, and we can say, well, these smaller capacitances probably won't kick in till higher frequencies, and we can estimate what are going to be the various impedance or low frequency impedances or resistances of these various nodes, and say things like, well, this output has got two drains, and so the early effect resistances are going to be sort of the dominant component there. Those are fairly large resistances compared to things like the incremental resistance of a diode-connected transistor that's carrying a comparable current, or the source conductance of a transistor that's carrying a comparable current. And so we can kind of get a sense that these internal nodes are going to settle much faster, or have much faster dynamics than the output node. And so we can kind of concentrate our modeling of the dynamics associated with the high resistance nodes and the large capacitance nodes first. And then maybe if we see something like an extra corner in the frequency response of a simulation that we're doing on the circuit, we can say, okay, well, this probably correlates well with the dominant pole that we see. But then, we might see something else and wonder, okay, now what could I add to the circuit to account for the various other twists and turns that the frequency response takes, whether it flattens out because you hit a zero, or whether it starts dropping off at a steeper rate because you hit a pole or something like that. You can say, okay, well now where could that pole come from, and try different things, putting them into your model and figuring out what parameters, what circuit parameters those corner frequencies are associated with. Okay, so in general, adding these capacitances in basically introduces extra places where current can be shunted away, and you pick up additional factors of current dividers and things like that, current divider ratios, as you kind of chase these current increments through the circuit. And so you can kind of ask yourself, at what frequency would this capacitor kick in? Well, it's gonna kick in at frequencies, or become significant at frequencies at which the impedance or admittance of the capacitor is comparable to the in magnitude to the conductance or the resistance, incremental resistance of the node that we're talking about. At frequencies above that crossover point, the capacitor will become more significant, in fact, and will steal most of the current away. And at frequencies below that, you can kind of think of the capacitor as not really mattering all that much to the calculation. You can leave it out. Okay, so that's all I really wanted to say about these internal capacitances. You can take them into account selectively, and they don't encumber things too much, but you only want to do it selectively. That's the basic take-home message. Okay, so I think that's probably going to be it for this segment. In the next segment, what I want to do is I want to talk about a heuristic, which is related to what we just talked about, that I use when I decide where to account for the early effect. And we're going to look at a technique that will allow us to increase the gain of something like the CurrentMirror amplifier from sort of a single-stage amplifier gain to something that's more like the product of two single-stage amplifier gains. And we'll see then.